Alright, welcome back everyone to another lecture in our data science course. Today we want to talk about the multiple linear models chapter in the lecture notes using map functions. But as I was designing the slides, I kind of noticed that the motivation is about doing multiple linear models, but really the chapter is about iterations in R, so how to do iterations without using a for loop. So this is why I kind of changed the title to multiple linear models via maps or also iterations in R. So this is what we want to do today. Let's look at our motivation again. I think it was in the ggplot chapter, I think chapter 2, where we were able to generate via stat-smooth easy straight line fits through a data set. In this case it was the Gapminder data, where we were comparing the life expectancy development over the years for 5 specific countries. And as you can see here, it's quite easy to fit a straight line through the points, and fundamentally by now we know this is nothing else than a linear model. So the question now becomes, okay, we can easily do it in ggplot, but where is the data? Where is the linear model object that we are used to if we call the LM function? And this is the drawback of only generating a linear model with ggplot. I mean, it's a good visualization, but we don't have the data. And the idea of this chapter now is to be able to generate that data and to collect everything in one place without using for loops. By now we know we could technically simply do a for loop, filter the whole data set for each country, then run a linear model and or the LM function to get a linear model, and then we have everything we need. But then it becomes tricky to collect everything into one place, and it's a bit more inconvenient. But with map functions it's quite easy to do everything in one go. So this is why we're dealing with this now, so we can get more fluent with the way with R and use map functions to do so. So the goal of this chapter is to do everything at once. So here you see that this whole generating the linear model thing can be done within one pipe, and you don't have to understand what is going on there now, but this is at the end of the chapter you will. And as you can see here, there are these map functions that help us to do things. And as you can see here, the result is one tibble, so it's collected all in one place. But in the end, we will use list-like columns. So as you can see here, the columns are not of type double or character or whatever. They are of type lists here. So fundamentally, in a tibble, we can collect all our data and we have everything in one place. And this makes working with the map function so easy. And we actually have only one pipe and we don't even need a for loop, and so things are more concise. And this is why it's actually, for me at least, enjoyable to use map functions instead of for loops, just to have everything concise and everything collected into one place. Okay, so but before we dig in, as always, I owe you a dinosaur, so it's dinosaur time first. Today I'm especially proud about this dinosaur. It's invincible now. It got these pliers now so that it can overcome its challenges with the small arms. So this is why now it's invincible and it can go nuts. I guess the only thing that can stop it now is a comet or something. But in any case, I'm really happy with this dinosaur. So I just wanted to mention that again. Okay, coming back to the real stuff we want to deal with. As I said, we'll encounter list-like columns, so we need to deal with lists more. And one thing what is nice about lists is that it's a really flexible container where we can throw stuff in and collect everything in one place. So as you can see here, I have created a list by nesting lists into it. So as you can see here, the first column, so to speak, of our list is called A, and it contains one string Wurst in this case, This example was inspired by the song Wurst oder Käse. It's a silly German song about sausage or cheese. In any case, it's the lyrics in there, so that's what you see here. The second column of this original list is a list again, so we have a list in a list. And as you notice, in this list here, we have strings again, so the lyrics of the song, but we also have some number. This is the great advantage of lists. You can collect different data types. You can collect numbers, you can collect strings, so characters in our speak. And yeah, and if you, for instance, call this str command, then you can see the structure quite nicely. So here again, it's a character vector in there as the first column, so to speak, of the list. And then the second column is a list again that itself consists of character vector, a one-dimensional character vector, and then a numerical vector. So we can collect everything in one place. And in fact, we have been dealing with lists all along. So tables are nothing but lists where the columns are enforced to be of the same length. But in general, they are lists, and this is why with tables it works to also nest lists in a list. This is how we get list-like columns. And that's really makes tables flexible, and this is why we can do stuff like collect all our data in a list and then collect it all in a table. And fundamentally we can collect our data, so our original data. We can, if we use grouping, we can easily create list-like columns by simply nesting it using the nest command, as we can see here. So we just take our initial data, we filter for the 5 countries we want to look at, then we group by country, then we simply say nest. And this way what it creates, or what R creates, is a new table where for each country the data corresponding to all other variables and so on for this particular country is simply condensed into a table, and this is done for each country, and these tables are collected in a list. So we have a list of tables, and that is collected then as a new column within our table. And this may feel weird at first, but it's really great, because this way we can now use data, this data column, as a new variable. For instance, for a linear model function, we can later on then say, okay, use this variable data to get your data, and then we just give another formula, and then it will run the linear model for each data set. This is fundamentally what we will try to do here. But before we talk about complex functions like LM, so linear model, let us figure out how this works with very simple functions. For instance, recall our example from our data wrangling chapter, where we're noticing that something weird is happening if we try to compute a minimum of 2 columns, as the resulting minimum is only one number. We noticed that it was happening because of this vectorized calculation. The minimum was being calculated for this whole vector comprising of all values of A, all values of B, put into one vector, finding the minimum, which is just this one number, and then recycling the value to have the length of the table or the table column. And this is what is happening here. And fundamentally, or if we want, you could use row-wise to compute this minimum for each row, but we could also use map functions. So before we move on to doing this for A and B, so with 2 arguments, let's look at an even simpler example for a function that only takes 1 argument. So for instance, looking at the minimum of this column A here and the number 2. So we want to look at this minimum function here, which just returns the minimum of a number A and 2. And then if we plug in the whole vector A, again, due to vectorized computations, we will simply get back one value instead of the minimum of each number in A compared to the number 2. But with map functions, we can easily do what we actually want to do, which is to apply this our arguments that are in the vector, our function A, to all arguments that are in this column A. So this is what the map function does. It takes arguments, so a vector of arguments, in this case it's the column A, and then it takes another function f, in this case it's this minimum function we have declared here, and then it computes f of a for each a in this original vector. And this is what the map function does. So here we can see that we get the correct result. We get the minimum of a and number 2. So a is 1 in this case, so it's 1. A is 2 in this case, and a is 3 in this case, so the minimum of a and 3 is 2, and this is why we get 2 back. Yeah, this is the idea behind map functions, simply applying a function over and over again for a set of arguments without using, so to speak, the vectorized computation, so kind of going around that. And so as to avoid what we have seen that happens if we just simply use mutate and then the minimum of 2 columns. What is maybe not so nice, I mean it depends on your case, is that the result here is a list now. As you can see from the output format, it's a list, but sometimes what we really want is now the resulting vector. So you want to get a single vector with 1, 2 and 2 in it, and with the map functions, so map is a function, I forgot to say, from the Perl package, which is part of the tidyverse, and this map function also comes with, let's say, brothers and sisters that that will enforce the outputs format. So for instance, if you want to get a string or a vector of doubles, then you simply use the map doubles function. For instance, map double, the rest of this is the same. So all of these map double or map character, map integer and so on, they all use the same syntax. It's just that they at the end give a different output. And yeah, so what we see here now is that the resulting or the result is a vector now instead of a list, which is sometimes preferable depending on your application. And what you see here still, which might be a bit annoying, is that you wanted to work with your tibble that contains these columns A and B, but you had to use this $sign to access the arguments you actually wanted to. But with mutate, you can actually avoid that, and this makes it such a great combination of 2 functions, because you can simply use the column names then, and yeah, you will get that result. So here we used map double, and therefore the corresponding column is a double column now. And yeah, now everything is stored in one place, which often helps to for further processing, because you have all your data there, and yeah, you know in what format and so on. So that's quite nice. But often here, as we did here, we have a specific function we want to apply, but in a lot of other cases we have a really simple function like, I don't know, just add 2 or whatever to a different value, which is not really something we want to save in a variable. We don't really want to define a simple function every time we want to do some really simple calculation, which is why the map functions allow us to define anonymous functions. So we don't need to declare them with a name or anything. We can simply define them anonymously with the tilde symbol. Let's see how that looks in this case. So here the same function, this minimum function, it's kind of a simple function too, can be defined using the tilde. And then we simply use the dot operator as an argument for that. So here we understand now this, or all of this, is a function now that takes one argument, and that argument is put into where this point or this dot operator is, and this map double will then sequentially apply the arguments that are stored in the column A. This is how you read this. And with that, we already have everything we need to complete our project with the linear models. So now we can simply use the map function to map, as I said earlier, over the data that we have created with nesting the tibble. And here we do this again with an anonymous function because there's no real point in defining a LM function that simply uses this data. It's a simple function, so why bother giving a name to it? So it's anonymous without a name. And yeah, so here we use the map function to map over the data. We're using the data column as arguments. So in this case, in each step of our computation, the argument is a tibble containing the data. So this is why we say data is equal to dot. So data is equal to our argument. And then here we simply say, okay, for each in each iteration, use the formula life expectancy explained by year. And this way we get a new column, which we call linmod. Just with the regular mutate syntax, we know what the new column's name will be. And here we see that it's a list-like column again now, and we have LM objects stored in there. As you recall, the LM objects are nothing but lists as well, storing all kinds of data with respect to our linear model. And yeah, so we had to use map here instead of maybe map double or map whatever. I mean, it's kind of clear that we don't use map double here because we know LM returns a list, but still it's important to realize that we cannot use any other map function here because what we get is not like a single number or a single character, and therefore we need to use map here. So it will be a list-like column. Okay. And now, if you want to get the coefficients, you simply do the same thing again with the map functions calling the coefficient function, or you could extract the slope or the intercept via map functions again. So here, for instance, if you want to get the coefficients into one column, which you call coefs, then you simply use the map function again. As argument, you're using your new linmod LM objects, which you stored in the linmod column, and then you apply the coefficient function to each linear model, which will give you back a double vector in each case. So here it's maybe less obvious that we couldn't have used map double. So we see here, well, the coefficient function here, this one returns the double vector. So you might be inclined to think, okay, I can use map double now because I want to get doubles. But the point is that map double only works, and map character and so on, it's the same for them. They only work if the return vector of that function is of length of equal to 1. So we can only, in this case, use map double if we get one number back, which will be the case very soon if we now want to, for instance, extract the slope from this coefficient vector. So here in each case we have now a double vector consisting of the intercept and the slope, which is why it's of length 2 here. And yeah, so we can easily get to the slope because we know it's always of that coefficient vector, it's always the second component. So we can easily use map double, apply as arguments you use the coefficients column, and then we say, okay, always take the second argument. We can do this by simply writing 2, but this is, I mean, you might be confused why this works. In fact, this is it's because just selecting a second component of a vector is such a common task that map comes with this shortcut. What is really behind this is like an an anonymous function again, you use the tilde, then you know, take the vector that you get from coefs, and then from that vector, take the second component. It's just a bit tedious to write this every time you want to do something like that. This is why there is this shortcut. But in the end, it's again an anonymous function. And you can do the same thing with using named vectors. You know that the coefficient function will return a named vector. So it will have the names intercept in parentheses, and it will have the name life_exp in this case for the slope variable, because life_exp is the variable we were regressing for. So for instance, if we wanted to get the intercept, we could easily use the same shortcut, but instead of writing 2, we simply write the name of the named cell in the vector. So in this case, we can, instead of writing again tilde, then take that vector you get, and of that vector you find the name intercept. You can simply write intercept into the map function. Yeah, and this is how we already achieved what we wanted to do. And again, we have everything in one in one tibble, collected everything in one place, which is nice. And we have everything in one pipe, so a chain of pipes, which also makes it concise. So it's it doesn't take a lot of lines of code. And in each step, if the functions you apply have meaningful names, you actually see what is done here. For instance, here you see, okay, in one line you see, okay, this is only linear model fitting, and here, okay, this is getting the coefficients and so on, which is quite neat. And overall, you don't even need a for loop for this, which saves you lines of code again. Yeah, so this is how we computed our linear models for different subsets of our initial data. And technically we could stop here because we have already covered what we wanted to cover. But of course, the map functions can do even more, and I want to cover those applications too, because this of course then enables us to do more in R. So let's see how we map over more than one variable. Going back to our initial example with the minimum, we can use the map_to function, which again also comes with map_to_double, map_to_character, and so on, so with its different versions for the different outputs. And here we used map_to_double, and the syntax is basically the same. It's just it uses 2 arguments now for the arguments that are later applied to the function we have here. And that's basically it. It works the same, and now we can see the result here is actually what we wanted to get in the first place, which is the row-wise minimums, which we see here. And of course, if you use more than one variable, so if you use 2 variables here in this case, you can still use anonymous functions. You simply use the tilde again, and then you use not the dot operator anymore, but the .x and the .y operator. So, for instance, if we wanted to simulate normally distributed random variables, say a vector of length 1, of length 1000, and we want to use different mean arguments or different standard deviation arguments for this rnorm function. Then we can simply collect all the parameters we want in a tibble. So here we want to have a random variable, normal random variable with mean 1, standard deviation 2. In the next case, we want to have a random normal variable with mean 2 and standard deviation 1, and so on. And using the map_to function, again here we cannot use map_to_double again because it will this function rnorm will return a vector of length 1000. Here we simply state, okay, the x argument is mu, the y argument is sigma, and then we define an anonymous function via the tilde. Using rnorm, n is the number of realizations we want, we keep that fixed, but the mean here depends on mu, and the standard deviation depends on sigma here. We define this using this .x and .y argument. It's basically the same, just you need something to differentiate. And so it's the same as the dot operator, but you need something to differentiate. So this is why you have x and y here. And yeah, as you can see here, we get a double vector now of full of realizations from the appropriate normal distribution with the corresponding parameters here in the tibble. Again, everything is collected in one place, which I think is really nice. And we can play this game even more. We could use more than 2 arguments. And for that, shockingly, there is not map 3, map 4, and so on. There is Pmap. So first, let us define a function that actually uses more than 2 arguments, which I have defined as PlotNormals. We don't see the definition of the function here, but I can still explain what this function does. It takes arguments mu and sigma, and it takes a vector of random normally distributed random variables. So here in this case, this would result in this plot. So what this function does, it draws a histogram of the normals that are given to this function, and it overlaps it with the density function of a normal distribution with parameter mu and sigma, so in this case with the density of the standard normal distribution. This is what this function PlotNormals does, and as you notice, it takes 3 arguments, so therefore we cannot use map2 if we want to apply different mean, different sigma, and a different realization of the normal distributions to this function. And again, as I said, we use Pmap for this, which uses a list as input. So if I need to define a list, so the arguments of Pmap are .l, which is the list, and .f, which is the function that is to be applied later on. And into the list I throw simply my arguments I want to use for that function. So here we have mu, sigma, and the normals. These are what is in my tip normals function, the one that I just computed. And then I state here that I want to apply this PlotNormals functions to each line. So what this does now is in this new plots column, it will save the GG object. So basically it will save the plot into in a list. It will collect all the plots in a list where the plots correspond to, well, each of these lines here. So what the PlotNormals functions will give you back. And because again this because plot is a list, we can easily access them via the $sign. And then we can, for instance, if we want to get the first plot, we simply access the list. So this will give us back the list of all plots, so of all ggplot objects. And if we want to get the first plot, we simply use these double brackets and state that we want to look at the first one. And yeah, this would be the first one and the first plot we've generated. And yeah, this is how basically Pmap works. So instead of having an argument for each, so in the map function having an argument as with map2, like an x argument, a y argument, we have a .l argument now, which is a list of all arguments to be used. And in this case, because my PlotNormals function has arguments mu, sigma, normals, we could simply use these here, because these are the names of the arguments that PlotNormal uses. As you can see here, mu, sigma, and normals. We can simply collect them in a list, and Pmap will know what to do. But of course, lists don't have to be named. They could be just collection of unnamed columns, basically. And in this case, we would need to define an anonymous function saying, use PlotNormals. For the mu argument, use the first column. For the sigma argument, use the second column, and so on. And in this case, this works with not dot 1 and dot 2 because that could be confused with floating point numbers. You will need dot dot 1, dot dot 2, and so on. So how does this work? For instance, take an example here, a list that, as you can see here, does not have a name. So if I wanted to name, for instance, this first column, I would have to say, right, name 1 is equal to, and then this number, and then I would have named the first column of this list. But I didn't, so they don't have any names. So if I want to use a function later on, I will need to specify which argument number is taken. So for instance, in this case, I simply have these 3 arguments here, and I want to compute the sum of the first 2 minus the third argument, and I can easily, again, do this with an anonymous function using tilde, and then I simply need to number my input. So dot dot 1 refers to these arguments, dot dot 2 to these, and dot dot 3 to these arguments. I think it's pretty straightforward and just a bit something you have to get used to, basically. And yeah, that's basically it. As I said, today is really more a technical thing about how to do iterations, but using this map function is really a powerful tool and will enable you to do a lot of things in R, and it really helps you to understand a lot of code from other people, because other people like to use map functions too, because, as I said, they are concise and they collect everything in one space, and together with mutate and list-like columns, we can achieve great things. And yeah, this was then the introduction to map functions, and that's all I wanted to cover today. And so this video was a bit shorter because the previous 2 chapters were longer. I decided to throw in a shorter chapter, so this is why this chapter is shorter. And yeah, so then see you next time, and let me know if you have any questions. Bye.